Okay, guys, welcome back. So now we're going to talk about the heat of formation in specific detail. Okay, awesome. Now we've actually looked at this in some kind of detail already. We did some of these calculations the last time, but we didn't call them standard enthalpies of formation, which is delta H, not F. So remember, this not means that it's standard. So standard conditions, we're either making one atmosphere for gases or 1 molar for solutions. And it's an F because it's a formation that we're looking at. So before we were looking at it for reactions, now we're looking at the delta H not formations. So when we look at the reactions, we're actually using those delta H not Fs to calculate that. Okay. So O2 gas at 1 atmosphere at 25 degrees has a delta H not F of 0 because that is its most stable form. So that is how we find it in nature. So that's what we're going to see. O3 gas at 1 atmosphere at 25 degrees C has a delta H naught F of 142.2 kilojoules per mole. Because that's what the energy it takes to add that third oxygen onto that. Now, based on that idea, the standard enthalpy of formation is the heat change that results when 1 mole of the compound is formed from its elements at a pressure of 1 atmosphere. These values can be tabulated and are shown in the exam handouts. Actually, no, they're not. They used to be, but they're not anymore. You will be given values that you can look at. And I actually haven't made them pretty, so they are here. You will get a copy of these, and I will let you print them off before the test. I haven't uploaded this yet, but you will get these because they're not pretty. So there you go. But that's what you're going to get. We can use the standard enthalpy values to determine the enthalpy of formation of another material using the following equation. Delta N times delta H naught F products minus delta M delta H naught F reactants. And this is exactly what we did. Remember, we had that products minus the reactants. We had to multiply it by the number of moles. That's exactly what this says. Okay, and it's the number of moles of each material that we're dealing with. So for each material that we have, we multiply by the number of moles of that material, add the products, and then subtract all of the reactants from that. N and M are the stoichiometric coefficients of each species, and delta is the sum of the enthalpy. So, epsilon is the sum of the enthalpy for all the reactants or products. And we actually did this last time. So we practiced this last time. We have done this. This is not really anything different. We just now know what this symbol means. Okay, so that's the standard enthalpy of formation. Okay, awesome. And standard 1 atmosphere or 1 mole. So we're going to practice again. What is the energy to make 1 mole of diamond from graphite? So I see that diamond is 1.90 kilojoules per mole. Graphite is 0. So if I want to take 1 mole of diamond, my product is 1.90 kilojoules per mole minus that 0. That gives me that total net is 1.90 kilojoules per mole, and it's 1 mole, so that's 1.90 kilojoules. That is not insignificant. So it does take a bit to make some diamond from graphite, okay? But that is how much energy we would need to do that. What's the heat of formation of N2O4 from NO2? So I want to take NO2, make an N2O4. I need 2 of those to be able to do that. My NO2 value that's listed here, NO2 is 33.85. And the N2O4 that's in this table is 9.66. So I'm going to take the 9.66 minus 2 times 33.85, and that's going to equal 9.66 minus 2 times 33.85, and that gives me negative 58.04 kilojoules. Okay, and that is per mole for that particular thing. So Since there's only 1 mole, I can put it as kilojoules per mole. But we really only want to calculate it as kilojoules for that reaction. What is the heated formation of liquid water from H2 and O2 gases? So I'm going to take H2 gas plus O2 gas and make some H2O liquid. My H2O liquid, if I look over here, is negative 285.8. Oxygen is 0, hydrogen is 0. So that means, since it's 1 mole, it's negative 285.8 kilojoules. Okay. And of course, that is products minus reactants. Cool, awesome. Let's see here formation of liquid water from H gas and O2 gas. Well, okay, if I have O2 and I want to make an H2O, I need 2 of those. So that gets my oxygen straight. That means that I need 4 of these H's. So my H2O, and I'm looking to make a liquid here. That's negative 285.8, because we looked that up last time. The O2 is 0. That 4H, remember we talked about this last time, is 218.2. Okay, so products, negative 285.8. And we have to multiply that by 2 because there are 2 moles, minus my reactants. And that's 4 times the 218.2 minus 0. That's actually plus 0 because we need to sum that. Okay, fine. Let's do this math. 2 times negative 285.8 minus 4 times 218.2. And that gives me negative 1444.4 kilojoules for that reaction. That's right. Yay, that was fun. See, I can do this. It's not so bad. Now, as far as equations on the test go, let me verify. I don't think that I gave that to you. And I don't see it anywhere here. So it doesn't say that the sum of the products minus the sum of the reactions, yada, yada, yada. And the reason that I didn't do that is because we're going to see that equation, that summation type of thing so many times between now and the end of this material that if you don't know it by the time you get to the test, you're in trouble. Okay? Because we're going to use that not only for the enthalpy, but also when we talk about entropy and free energy. So we're going to have a lot of uses for that particular equation. So questions about that? Hopefully not. So calculation of delta H dot F. Now, the direct method is what we have been talking about. Okay, so delta H on F for CO2 gas minus the delta H for the C graphite plus delta H on F for O2. That's how we've been doing this. Now, there is another method that we can use, and it's called the indirect method. So it's used when a material is not made directly from elements in their standard states. Sometimes we just can't do that. There's no way for us to do it. So we can use Hess's law. When reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. Okay, so it doesn't matter how we get between point A and point B, the enthalpy is still there, right? So it's a state function, so we can do that. So as long as we can break the reaction down into smaller reactions that have measurable delta H naught reaction values, we can use those values to determine the enthalpy of our overall reaction. So we have a desire to know the enthalpy for C graphite plus half an O2 going to CO. Okay. However, this reaction also produces CO2, so it's not useful to determine the enthalpy since there's more than one product. Okay, so what are we going to do? Well, there's a way we can deal with that. So instead, we can use the following equations to determine the enthalpy. So C graphite plus O2 gives me CO2. CO gas plus 1/2 of an O2 gives me CO2 as well. I have delta H for both of those. If I reverse the second equation, I get CO2 goes to CO plus half of an O2. Okay, and of course I reversed it, so I changed the sign on the delta H. That's what's going on right here. And then I can take and add those together. So the C graphite plus the O2 goes to CO2, and that's that negative 393.5 that's right here. Okay, so I just copied that. And then that second equation, the CO2 gas goes to CO gas plus 1/2 of an O2 plus the positive 283 that we got from reversing this reaction right here. Okay, so that reversing. When I add those together, the CO2s cancel. I have C graphite plus, and look at that, there's half an O2 there, so that leaves you with half an O2 here, because I have to cancel that. So C graphite plus half an O2 goes to CO gas, and so if I sum these values, I get that value, and that's negative 110.5. Okay, so that's what we're talking about when we talk about that indirect method. In case you want a graphical representation of that, that's what we're talking about over here. So I know going from graphite and O2 to CO2 takes a 393.5 kilojoules, but going from CO2 to CO plus half of an O2 is only the negative 283. So the difference there is that negative 110.5 that it takes me to go directly from C graphite plus O2 to CO plus half an O2. Okay, so that's cool. Go awesome. Questions about that? Questions, comments, problems? I hope not. That is the indirect method. That is one way that you may be asked to do this. Sorry. I'm so sorry. I managed to get through the entire lecture last time, I swear, without doing it. And I'm really sorry about that. I know it can be distracting. So, a little bit of practice. So, what am I looking for? What am I trying to find? That's a darn good question. I didn't exactly put this as a nice little do this, did I? I did not. I know that I'm looking for something that's related to this. I have two AO solids there. Fe2O3 there. 2Fe plus Al2O3 and 2Fe. Yeah, no. At the moment, I can't remember what the hell I was trying to have you do. So I'm going to have to sort that out. And I will put this on D2L when I go through the after in-class problems. So I'll do it then because I'm not sure what I was trying to do here. So I'll figure it out. Sorry. Here, the reaction of acetylene C2H2 with hydrogen H2 can produce either ethylene C2H4 or ethane C2H6. What is the delta H for the reaction of C2H4 with H2 to make C2H6? Well, I only have this reaction here where we make C2H4 directly, and then this reaction here where I make C2H6, and I want to know what energy does it take to get between the two of those. Well, that's really interesting now, isn't it? Because what I can do is I can take and I can subtract this right here. And if I do that, that gives me a C2H2 H2 going to C2. I think that's on. Oh, sorry, wrong one. Hold on, sorry. C2H4 C2H2 plus an H2. That delta H is positive 175.7 because I reversed it. So I've changed this first one to give me that. And when I do that, I then take this C2H2 gas plus 2H2 gas to give me C2H6. This delta H equals negative 312.0. And of course, these are kilojoules per mole. Cancel the C2H2s. I cancel one of those H2s. That gives me that C2H4 gas plus an H2 gas going to C2H6 that I was asked about. That's the equation that we're talking about right here. What is the delta H for C2H4 with H2 to form C2H6? So I sum those two values, and I could do that on my calculator. 175.7 minus 312.0, and that gives me negative 136.3 kilojoules. Cool. I can do that. That's an indirect method. So there's that. For your exams, both the direct and indirect method of determining delta H may be used. Tabulated values can be used to do this. You will be expected to know that the most stable form of a delta has a delta H, not F, of 0. And that means you need to know what the most stable form of a compound is. Common things you should know: O2, N2, H2, F2, Cl2, Br2, I2, and C graphite. Those are the ones I expect you to know, because you may not see those in those tables. I expect that you know that those will be 0. Okay, you may note that these things appear in some of these tables as 0 values, so you may not need to memorize them. They may be present, but you need to explain why they're there. Why is that the value that they have? Because I may ask you about that. Okay, so since it's the way that it's most stable in nature, that is defined as 0. Okay, so questions about that? Hopefully not, but if there are, you know how to reach me. All right, what is the next thing we're going to be talking about? Phase changes. So I'm going to take a break, and I will be back with you shortly. Thanks, guys.